In today's video, we're going to learn about one of those key modules that everyone needs to know, the OS module. We'll cover quick attributes and functions, dealing with environment variables, executing commands, and even forking in pipes. My name is Jake, and this is the Python Standard Library. OS, short for operating system, is packed with functionality that allows you to interact with your operating system in various ways. One quick note is that I won't be covering os.path or anything related to paths in this video, since all of that functionality is included in and handled better in the pathlib module. I'll put a link in the description and in the top right now for my video on that. Starting up, of course, we need to import the OS module. And as you can see, there's a lot in this module, the vast majority of which you're never going to need, but there are some interesting things that we are going to cover. The first up will just be getting some information about the system that you're on, the most basic of which is os.name, which right now this mostly has one of a few different options. For myself, it says POSIX. That's because I'm on a Linux operating system. If you're on a Windows system, you'll see Windows, and if you're on Mac, you should see Mac. You can also determine the user that you're logged in as by running os.getLogin, and we see that my current username is Jake. You can also get more information about the operating system by checking something like os.uname, and this gives us some interesting things, like the sysname being Linux, the node name, which in many cases would be the host name. We can see some kernel information, as well as some other interesting things, including my system architecture. You can also get things like the CPU count, so you can make a smarter determination of how many processes you want to split into if you're doing things like multiprocessing. And finally, for the quick things, we can use os.getRandom to get any number of random bytes that you want for whatever reason. Some people use this for things like cryptography, but it's not really good for doing things like random string generation, because a lot of times when you're trying to decode it, it's going to give you bytes that can't really be decoded correctly. Next, let's talk about environment variables. So if you're not familiar, you can think of environment variables kind of like constants that just live on your system. For most people, there'll be a lot of different kinds of environment variables that have been set from different kinds of things. And you can also do things like explicitly setting environment variables when you're about to run some type of command. So here I'm going to set an environment variable called myenv and have the value of it be 17. So when I run ipython, we can look for that environment variable and check out the value. Now, the interesting thing about environment variables with Python is that as soon as we import OS, it reads the environment variables on the system and populates it into this os.environ object. And as you can see, there's quite a few things here. And at the very top is myenv, as well as some other interesting things. Since this is running on a Python container, it's significantly less than you'd see on my actual system. But because I have some sensitive information in my environment variables, we're not going to expose all of those. We can see information about the kind of shell that we're running, the system's hostname, Python version, our current directory, and significantly more. And while this looks like it's a dictionary, it's actually not. It's actually an instance of this os.environ class, which if we take a look at that, we see that it is a mutable mapping, which is pretty similar to a dictionary, but it does have some additional behavior that sets it apart from a classical dictionary in Python. If we take a quick look through its source, we can see, yes, it's inheriting from mutable mapping, and it does define different behavior for things like get, set, and delete item. Okay, so there's some different ways we can interact with the environment variables on a system. The first being something like os.getEnv, and we can put in the key name for some type of environment variable. In here, we see the host name for this container is py.latest. We can also try to add additional environment variables using os.putenv. And here we're going to put a new test environment variable with a value of, creatively enough, value. Now, if we use getEnv to get that value back out, we don't see it there. Why is that? Let's take a look back in the os.environment and look for test in here. We don't see it in the top or the bottom. That's because putenv doesn't directly modify the environment you're in, but the modifications will carry over if you use something like os.system, popen, or fork, as well as the exec_v functions, which we'll get into most of those later. However, if you do want the environment variables to be updated immediately, then use os.environment directly. Here we can treat it basically just like a dictionary, setting test equal to value. And if we try getEnv now, we see we have value there. And if we check os.environment again, we see at the very bottom here, test and value. These will also be reflected in system, popen, fork, etc. because not only does it update its own data structure, it also calls putenv. This is why most of the time I don't even use something like getEnv or putenv. I just interact with os.environment directly like it's a dictionary. For example, if I wasn't sure that test was an environment variable in this context, I'd run os.environment.get test. The system function is one of the more basic ways to run some other command. The usage of system is pretty easy. Basically just accepting the string for some kind of command. In my case, when I run this, it brings up the gnome system monitor. And notice that it'll keep blocking the execution of this script until I close that out. And finally, when I closed it, it returns. Now, a couple interesting things here is that we do see some output here, but that's not really coming from our script, right? Because we're not printing anything or logging anything during its execution. What you're actually seeing is the process that we started for gnome system monitor sharing our standard output. Now, you don't really get much back from os.system. What you can get is, say, the status code. So if we run this again, it again launches gnome system monitor. Then we close it, and we see res is equal to 0, which is a common exit code when things exit cleanly. Now, there is a way to capture standard out from what gets executed, so the first person to comment a working solution will get pinned. Good luck. Now, beyond that potential solution, there are alternatives to using os.system, especially if you care about getting output or providing input for some type of program. And for that, we're going to use os.popen or pipe open. And this is going to operate somewhat similar to os.system. The difference this time is when we execute something like ls-lah, we can interact with that process pipe. The default pipe that we get is a read pipe. So we can get the output of that command by running process.readLines. Now we could just call read or whatever, but I think read lines is going to be cleaner here. We'll also go ahead and close our pipe to the process. And what we can do is we can iterate for each line in that output and simply print it out. And I'll also put a strip at the end of there. Just get rid of any extra white space. And what we're expecting this output to look like is basically the same output as we see here. So let's give this a shot. We run Python command IO, and yeah, that's exactly what we see. And just to prove that we are printing this line by line, we'll just put some separating characters there and run it again. And here you see, yep, we're printing out each line of that output. Pretty nice. But not only can we open a pipe that can read the output, but we can also open a pipe that would write input to some type of process. So now let's create another process. And this will also use popen. This time we're going to run the wc command, and we're going to open that pipe in write mode. We're also going to specify that it should be buffering at up to 1024 bytes. Next, we're going to call process.write this time, and we're going to pass in some text for it to count. Here we just have a string with some words in it and some line breaks in it. Next, we're going to run process.close again. And just to make sure we're not muddying things up, let's temporarily comment out what we had up before and then run this. And here we see something interesting, is even though we're just writing the output here, we're still seeing something being printed out here, right? Well, think back to when we were running GNOME System Monitor. We weren't actually getting the output from that command. However, it was sharing our standard output, which is the same thing that's going on here. We can't get that information out through this process here because we have a write-only pipe. However, we do see it printing to our standard out. So while os.popen is nice for when you want to provide specific input, or if you want to get output from some type of program, you can't really do both at the same time. But for simple cases like these, it's pretty nice. Now, there is a better way in Python to run some type of command, not only provide input, but also get the output from what you're executing. And that's by using the sub-process module, which may be our next stop in the Python standard library tour. One of the lesser known, but more interesting features in the OS module is fork. Now, how os.fork works is when your program executes this function, it's going to split itself into two and give you back a PID. And those two separate parts are what's known as the parent, which has been the main execution process up until this point, and the child, which is a new process that will continue on when you forked. Now, crucially, this is also going to give you a PID, and you're going to get a different result depending if you're the parent or the child. The value of PID here for the parent will be the new process ID for the child, whereas the PID value for the child is just going to be 0. So with this in mind, we can check if we're the parent by running if PID is greater than 0, or we can simplify that even further by just saying if PID, because in this case, a non-zero PID means that we're the parent, and then the parent can do something. In this case, the parent is going to sleep for 5 seconds, and then we're going to use os.kill, pass in the PID of our child, and send a signal of 9, basically telling it just straight up kill. Okay, if we don't have a non-zero PID, that means that we are the child. So we can do something entirely different than the parent would do. In this case, we'll do, say, an infinite loop. And in here, we're just going to say something simple like child running. We'll then only sleep for about 1 second, and that's it. Lastly, we'll print off finished. And at the very start of the script, we'll also print off that we're starting. Okay, let's run this. Let's see what it looks like and then talk through the execution here. Here we see it starting. The parent is waiting for 5 seconds for the child PID. You see the child print out that it was running, and this does it 5 times, which makes sense. And then finally it's killed and we see finished is printed out. So let's trace the execution for each. The parent process runs everything up until this point, just as it normally would. From there, it does the check to see if it is a non-zero PID. It is, so it enters this block under the conditional check, prints out that it is waiting 5 seconds for its child. It then sleeps for 5 seconds, and then finally calls kill on the child. Meanwhile, the child starts at this point. It still has all the context of program execution up until this point, though. It checks if it is a non-zero PID, which it isn't, so skips down to this block here. And here it enters what it considers to be an infinite loop, where it's just going to print that it's running, which we see it prints out 5 times. Now, unfortunately for the child, the parent takes it out. So its execution stops in this loop. And then the parent continues on and prints out finished. We can further clarify this by putting an F string here and say PID is equal to at the very end. And if we run this, we should see when it prints finished, that same PID printed out. And there we go. Now, os.fork is something that I do use in one of my projects at work. So let's take a look at that real quick. Okay, here we see a helper function called fork broker. And what this does is pretty simple. It forks the program execution. The parent process lets the user know that it's going to be running broker in the background and gives the user the PID of that background process. At this time, the parent process exits completely. So it's the child that then picks up execution. Here we take care of adjusting the log levels from there. Now this is used in a couple of places. One of the first places is in this helper function here called handle keyboard interrupt. So at any point, if a user presses Control-C while this program is running, it's going to prompt the user to ask if they want to run this program in the background, if they want to kill it, or just resume execution. If they choose to run it in the background, then it calls that fork broker helper method. This allows the program to keep running until it completes, but also freeing up the terminal for the user. Now, this helper method is also used specifically in the CLI. So if a user performs some type of action and passes a background flag, then we use that forking behavior to just immediately execute it in the background. Pretty nice. Okay, that's great that we can spin off a child process, but what if we wanted the parent to alter the behavior of the child, or if we wanted the child to report something back to the parent? We would need some way for them to communicate. Well, one way we can achieve that is to use pipes, also in the OS module. Now, when you create a pipe, you're going to get two things back. And that's going to be a read descriptor and a write descriptor, allowing us to read from and write to that pipe. Now, it's at this point that we're going to call os.fork, because in our parent, in this particular case, we want to go ahead and close out the read end of that pipe. And in our child process, we want to close out the write end. That's because in this case, the parent is just going to be telling the child what to do. So it's going to be using the write descriptor to write to the pipe, and the child is just going to be reading from the pipe with that read descriptor. Now for this parent, what it's going to do is it's going to iterate for each value in that list of values. It's then going to tell us that it's sending that value to the child, and it's going to send it by calling os.write. We're going to be writing to that write descriptor and passing in the result of value.encode to send bytes to the pipe. Next, we'll just go ahead, call time.sleep again, just to slow things down a bit, and finally call os.close on our remaining write descriptor. And if we just want to be sure that we're not getting ahead of ourselves for completeness, we'll call os.wait to wait until the child has exited. Now, on the child, again, we're going to use that infinite loop. We're going to pull that value from the pipe using os.read on that read descriptor, and we're going to read up to 1024 bytes at a time, and then we're going to decode the value to get it in a nice usable string. Then we're going to print off that the child received that value from the parent with the value itself, and if the value is equal to exit, then we're going to print off that the child is exiting, break from our loop, and then finally call os.close on our read descriptor. That's a bit, right? Now let's make sure that it works by running it and see what everything looks like. Okay, we see that the parent is sending a value to the child and the child is receiving it. That continues until it sends the exit to the child, which the child receives and exits. Perfect. So that's behaving exactly as we expect. Now, one crucial thing here is make sure that if you're going to try this, you create your pipe before you fork. Otherwise, if you were to reverse this and try to run it there, it's not going to work. And that also gives us an orphan process that we then have to hunt down and kill. Now, the reason why this doesn't work is because after you fork, os.pipe is going to give you a different pipe for the parent and the child. So they can be speaking and listening to completely separate things. So make sure that you create your pipe before you fork. That's what lets the communication flow correctly. And that wraps up this video. And this stop on the Python standard library tour. There's a ton more the OS module has to offer, but these are the parts that I believe are most commonly useful. However, if there is anything you want me to cover specifically, let me know. If you learned something new, please consider subscribing to the channel and sharing this video with your friends. If you have any questions or comments, please leave them in the comment section below. And as always, thanks for watching.